Okay? And to find the distance between 2 points, we don't just want to graph it and count, because when we count, these points are going to be diagonal from one another. And so if I were to graph something, and I put a point down here and a point down here, I can't just count between those 2 points and say, this is 6 units long, or whatever. If it was vertical or horizontal, I could count, right? But if it's at a diagonal or has a slope to it, we can't count how long that segment is. So we have to have a way of being able to find that segment without being able to just look at the graph and know what it is. So the formula that we're going to use again today, that we've already used this year, but it's going to come back today. X2 minus x1 squared plus y2 minus y1 squared. Call that the distance formula. Okay. Earlier in the year, we talked about distance and midpoint and did some different things with ordered pairs. Today is coming back to the distance formula, and we'll talk about why we're going to talk about it today here in just a second. But whenever we label these 2 points, x1, y1, x2, y2, is our 2 ordered pairs. And it doesn't matter which one's which. Okay? This could be the first one, this could be the second one, or they could be flip-flop. Doesn't matter which one's first and which one's second. But we're going to plug that into our formula. And you got to really be careful of the signs here. Probably the signs are the things that get missed more than anything else, because this is subtraction between these. Also, make sure that you subtract the x's. One thing is, some people try to put these two together and these two together, and that's not what gets put together. It's x2 minus x1. So this is going to be 1 minus negative 3, which is really 1 plus 3. That's why you got to watch your signs, because we're subtracting a negative, which makes a positive. And then we're going to do y2 minus y1. So that would be negative 3 minus 2 squared. One plus 3 is 4. 4 squared is 16. Negative 3 minus 2 would be negative 5, but when I square negative 5, what do I get? Okay, make sure when you put that into your calculator, and it kind of depends on the type of calculator you have, but when you square a negative 5, you want to make sure you square the entire thing. And for a lot of calculators, you have to put parentheses around it, because when I square a number, I should always end up with a positive answer. A negative times a negative is a positive times a positive is a positive. So whenever I square a number, I always get a positive. And then we take the square root of each one of those, and we get the square root of 40. Or add those together and take the square root of it, and we get the square root of 41. We can leave our answer a couple of different ways. Square root of 41 is what we call our exact answer. And then we also talked about how we can put it into a decimal if we wanted to. And we could take the square root of 41. And if we take the square root of 41, what do we get? About 6.4. Okay. And our label here that we're going to talk about is units, because units is just a generic label that we use. Like when we talk about a coordinate plane, we say how many units long is this, and when we did like area and perimeter earlier on a coordinate plane, we talked about units, and so U is just a generic label we talk about when we're talking about plotting points on a coordinate plane. Okay, so why do we need to know distance formula again? Well, today, what we're going to talk about, it says the distance from a point to a line is the length of the segment that is perpendicular from the point to the line. So if I'm up here at point A, and I say, what's the quickest way to get to this line? Okay? It's kind of like, let's say I'm going to go from here to Hutch, right? Well, there is no direct path from here to Hutch. Now, if I was flying, there would be a direct path, right? But there is no direct road that goes from here to Hutch. You got to either go down to Medora and then take the highway, or you got to go down to 30th and go over. So that's not a direct path. So the direct path is the most direct, easiest, quickest path to go if that is available to us. Well, when I'm drawing a line, that's going to be available to us, right? And so the shortest distance from this point to this line is the distance that is perpendicular to that line, okay? These two are going to both be a little bit longer segments. And so in this case here, it says find the distance from A to BD, okay? A to BD. So BD is going to be this line right here, line BD. And we're going to find this length right here. So the length that we are finding here is AC. And remember, if we don't put a symbol above AC, what's it mean?
It's
Distance, right? Distance from A to C. So we don't want a symbol above AC because we're talking about how far it is from A to C. So the two ordered pairs that we're going to use are negative 3, 3, because that's A. And then we're going to do 1, negative 1, because that is C. So those are the two ordered pairs we want to use. We don't use B and D. We're going to line BD, but we're going to go to C because that's the shortest path to go. I'm going to label this X1, Y1, X2, Y2, and like we said before, it doesn't matter which one's which. If you labeled this one as X1, Y1, that's okay. You're going to get the same answer. So we're going to go 1 minus negative 3, which is 1 plus 3 squared. And we're going to go negative 1 minus 3. So this would become...
Just expect me every day.
I should, yeah. When you don't show up, I'm going to start worrying about you. So 1 plus 3 is 4. 4 squared is 16. Negative 1 minus 3 is negative 4. But when I square it, once again, I get a positive 16. 16 plus 16 is 32. And it doesn't really say how to leave our answer here. So either one of those are appropriate answers. It just kind of depends on how they ask us to leave it. If they ask us to leave it as a radical, we'll leave it as radical 32. If they ask us to round it to the nearest 10th or 100th or whatever, then we'll put it in as a decimal and we'll round it to whatever decimal they ask us to round to. Okay, so both of those would be appropriate depending on what we're trying to do. Okay, so on this one here, it says which one is different. Okay, which one is different? Find the distance from point X to WZ. So here's point X. WZ is this line right here. So when I find the distance from point X to WZ, which segment would I want to use? XY, right? I want to go from X to Y. I want to start at X, I want to go to Y because that's going to be the shortest distance. These are going to both be a little bit longer to get to, okay? So distance from X to YZ is the same as the length of XY, which is also the distance from line L to point X. And we say line L because there it is, right? Line L to X, that's the shortest distance. So the one that we don't want is XZ, because XZ is this distance right here. That's the one that's longer. The other three are all the same thing. They all say it in a little bit different way, but they're essentially saying the same thing. XZ is the one that's different, because XZ is talking about this. The other three are all talking about this segment right here. Okay? So whenever it asks us to find the distance, we're always going to find the shortest distance. Okay? And it's always going to be that perpendicular one. And we know it's perpendicular because it's 90 degrees. Okay, and we know that 90-degree angle is there. So if you find that 90-degree angle, we know which one we're trying to use. All right. We got some more theorems today. Okay. First of all, a perpendicular bisector. We've seen the word perpendicular. We've seen bisector before. So now this is a perpendicular bisector, which does both things. Perpendicular means what? Which means what, Adrian?
I don't know, I just know the sign.
You know the sign, okay? It crosses, but not only does it cross, what's special about where it crosses? 90 degrees, okay? So it's 90 degrees. How do we know that for sure it's a 90-degree angle? makes that little square, right? So this little square right here tells us that it is going to be 90 degrees. Okay, so perpendicular means 90 degrees. Okay, the symbol for perpendicular is that upside down T. Okay, I'm just going to keep throwing that in there because we're going to see that sometimes. Okay, what does it mean to bisect something? We've seen that a couple of times this year. Well, let's break down the word. What does it mean to bisect? What does prefix bi mean? Two. What does it mean to sect? Like an intersection. It crosses or cuts, right? So where do these two lines cross and cut it into two equal parts? Bisect. And then once again, notice my symbols here. These two pieces, PM and QM, are both marked as congruent, right? So we know that those two pieces are congruent. We know that it's being a 90-degree angle here. So we know PM is equal to QM. And we know that line N is perpendicular to segment PQ. Those two things are true. And we know that because of the markings on the picture. Okay? And so it's just a way for them to show us or tell us that that information is happening. So we would say that line N is the perpendicular bisector of segment PQ. Not only is it perpendicular, but it is also bisecting it, splitting it in half. Okay? The next one, linear pair. Somebody asked me yesterday on the city map, one of the pairs that we had to mark on the map was a linear pair, and we hadn't seen that for a while. But once again, when I break down the word, linear means what? A line, right? Pair means two. So it's two angles that make a line. What they have to be is they have to be adjacent to each other. They have to be right next to one another. Okay? So what this theorem says, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular, right? So if I tell you that these two angles are both congruent, if I tell you angle 1 and angle 2 are congruent, what else do angle 1 and angle 2 have to do? In order to make a linear pair. What'd you say, Xander? They have to make up 180, right? They have to make a line. So not only are we saying that angle 1 and angle 2 are congruent here, they have to make 180. Well, there's only one way for that to be true. In order for these to be congruent and to make 180, what do the two angles both have to be? They both have to be 90, okay? And right now we don't have the square in the corner, but I know that angle 1 and angle 2 must both equal 90 degrees. Okay? And that's what it's kind of concluding here, is that it's perpendicular. And the fact that it's perpendicular, we see that symbol again, that upside down T, that means that they are 90 degrees. They didn't mark that right away because it didn't tell us right away that they were 90 degrees. We've come to that conclusion based on the theorem, but it didn't tell me that information right from the start. Okay? So that's why the square is not in the corner immediately. Now, for what I know, what I could now do is I could say these are both 90, and I could go ahead and make a 90-degree angle marking. Okay. Okay, perpendicular transversal theorem. So this is kind of where this ties into what we've been doing. Okay, H and K. What do we know about H and K right now? Looking at the picture. They're parallel, right? We see these two arrows. That means these two lines are parallel. Okay? J, what is J right now? What could we say about J? What do we notice in the picture? J is what? What's this telling us? It's perpendicular to H, okay? So if H and K are parallel and J is perpendicular to H, then what do you think J and K's relationship is going to be? It's also going to be perpendicular, right? And here's why, guys. Because if this is 90 degrees, what kind of angle does this have to be? 90. Why? Because what kind of relationship are those angles? What's the name for that one? Corresponding. Okay, those are your corresponding angles. And what we know about corresponding angles is they are congruent as long as we have parallel lines. Okay, so if H is parallel to K and J is perpendicular to H, these two things have to be true, then J is perpendicular to K. And we would say something here along the lines of corresponding angles are congruent. Because we know we have parallel lines, and because we have a 90-degree angle here, this one here also must be 90. So we're really using corresponding angles to kind of get there. Okay, we don't necessarily use corresponding angles or say anything about it in the theorem, but that's what allows us to get there. Okay, the last theorem here is the lines perpendicular to a transversal theorem. Okay, if M is perpendicular to P and N is perpendicular to P, so this one now is kind of the opposite of what we just talked about. What do you think we can conclude about M and N? That they're parallel, right? So this is kind of like what we did earlier, right? And last week when we were talking about this, we said if corresponding angles are congruent, then we know we have parallel lines, right? Well, here we know corresponding angles are congruent. They're both 90 degrees. So if these two angles are both 90, that means M and N must be parallel. So if M is perpendicular to P and N is perpendicular to P, and both of those are marked as 90, then M is parallel to N. Okay, so here I could say something like this. If corresponding angles are congruent, then we have parallel lines. Thank you. So that's kind of the statement that we are allowed to use here, okay? We're going back and we're still using the things that we talked about early on in chapter 3. But now we're putting together with perpendicular lines, okay? And so today is going to be a lot dealing with perpendicular. We keep hearing that word over and over again today. Perpendicular and parallel. All right, so in this proof, what we're doing is we're proving the perpendicular transversal theorem, okay? So when we prove the perpendicular transversal theorem, we can't use the perpendicular transversal theorem. We can't say this is true because of the perpendicular transversal theorem. I can't say, oh, look up in the sky, that's a plane. I know that because it's a plane, right? Well, we know it because we know what a plane looks like, we know what it is, and we could define what a plane is. Same thing here. We can't use a theorem to explain the theorem. So we have to prove why the perpendicular transversal theorem works. Okay, first step, H is parallel to K, J is perpendicular to H. That is our given information. Okay, as of right now, if we ever miss step 1 on a proof, that means you're just not paying attention, right? Every time that we've seen a proof, it's always been given. That may not always be the case, but for right now, that's all that we've seen. Okay, step 2. How do we know that angle 2 is 90?
I'm having trouble with the connection. Please try again later.
Was she trying to answer the question?
I guess.
She wasn't able to answer why it was 90.
Yeah, I know, she's not very smart.
It's 90 because it's marked.
Okay, it's 90 because it's marked, that's true, okay? But if I didn't have a marking here, what would I be able to say? Yeah,
Definition of perpendicular.
definition of perpendicular, yeah. And they went ahead and marked it, okay? But we know that that marking should be there. We know it's 90 degrees because we know what it means to be perpendicular. Good. Okay. Why are angle 2 and angle 6 congruent? They give me the statement. I have to say why. Corresponding. Yeah, perfect. And you could say the corresponding angles theorem, or you could give me the statement. This is what we talked about last week. You can either give me the theorem, but if you can't remember the theorem, you could say if we have parallel lines, then corresponding angles are congruent. Hey, I know this is a little bit longer, but you're just stating why, okay? And that way you don't have to worry about naming the theorem itself. I would accept either one of those. Either one of those are perfectly fine for me. I know naming the theorem sounds easier, but we're not always going to remember all the names of all the theorems that we talk about all year long. But we can remember the why. Okay, angle 2 is equal to angle 6. Now, notice this, okay? Here, they said they were congruent. Here, they're saying they're equal. Okay? We haven't talked about this one for a little while. We talked about this towards the end of chapter 2. And so I'm going to go ahead and give you this one because we haven't seen this one for a while. This is the definition of congruency. The other thing that's different about this, what does this little m right here mean? When we see that m, m means what? Measure. Measure of angle 2. Okay? So up here we said measure of angle 2 is 90, and now we say angle 2 and angle 6 have the same measure. So if angle 2 is 90, what's angle 6 got to be? 90. Okay? And we are using the transitive property. Bless you. Okay? If those two are, if angle 6 equals 90 and angle 2 is equal to angle 6, I would also say you could probably use substitution here. I would, because you could just substitute 90 in. And so I would say substitution property would also be a possibility here. Sometimes there's maybe more than one way that you can prove something. This would be one of those places. Okay, and finally, why do I know that J is parallel to K? Okay. What are we saying right here? What do we know about angle 6 now? It's 90, right? And so what I could do right here is I could now go ahead and put in my 90-degree marking, right? And if I see a 90-degree marking there, what's that mean about J and K? They are not parallel, perpendicular, okay? So we now know J is perpendicular to K because of, once again, the definition of perpendicular. If I see a 90-degree angle being formed, I know those two things are perpendicular to one another. Okay, I know they have made perpendicular lines. Okay, I think it's a little bit easier when they give me the statement. If you have to come up with the statement in the reasoning, that's a little bit harder proof to come up with. Okay, I know this one's kind of hard to see, so you kind of have to look at yours a little bit harder because it's in black and white. In this case, we have three 90-degree markings. Okay, we have three 90-degree markings. So, first one says, is B parallel to A? Are B and A parallel? So if this is 90, do I immediately know this is 90? No, only if they're parallel. Right now we don't know that for sure, right? If I had arrows on here, then they would be corresponding angles, and we could say, yes, they would be 90, okay? But if I look down here, what kind of angles do we have? Right angles, okay? And what do, not only are right angles congruent, but what kind of angles would these two be here? What would be the name for them that we talked about early in the chapter? What kind of pair of angles are they? Consecutive interior, very good, okay? Because here, A and B are my parallel lines, because those are the two that we're talking about here, right? B and A, and then D is my transversal. So these two angles are consecutive interior. What has to be true about consecutive interior angles? They have to be what? Not the lines, the angles. They have to be supplementary, okay? So does 90 and 90 make 180? Yeah, right? And so here, we would say yes. And our reasoning I know it doesn't ask for a reasoning here, but I'm going to go ahead and give it anyway. And we're going to say because consecutive interior angles are supplementary. Because they're both perpendicular to D, those two lines would both be parallel. Okay? What about, is B perpendicular to C? Okay, is B perpendicular to C? So what we now know is this. We now know we just proved A and B are parallel. Now that I've proven A and B are parallel, because at the beginning we said we don't necessarily know that these are both going to be 90, right? Because we don't know these two lines are parallel. But guess what we just proved? Those two lines are parallel, right? Now that we know these two lines are parallel, what can I say about this angle right here? Durston, what do you think?
I guess it'd be like, yes.
Okay, that wasn't the question. The question was, what would this angle be?
Oh. I don't know.
Okay, got to pay attention, okay? So if this is 90, what kind of angles are these two right here? What's the name for this pair of angles?
Same side.
They are on the same side, but one's inside and one's outside. Corresponding, good, okay? And what do we know about corresponding angles? They're congruent, okay? So we know these two are congruent, and so once again here we would say yes, and we would say because if we have parallel lines, then corresponding angles are congruent. Okay, so we kind of went in a roundabout way. We weren't able to prove this immediately at the beginning, but after we proved the first part, then we could prove the second part. All right, the last one for today. Take a look at this, and let's see what we think. Look at the information that's given. Hannah?
All of the vertical angles will be congruent, so we already know that the opposites of the two that are marked are 90. And then because of that, on the same lines, the corresponding angles will also be 90, and then their verticals will be 90.
Okay.
And that just lets us mark all the angles as 90.
So here's the part that's a little tricky on this one. Are M and N parallel?
We don't know yet.
We don't know yet.
But
What about R and S?
we don't know that
We
yet.
don't know that either. So if this is 90, can I immediately prove that this angle's 90? Not right away, right? Because if R and S are parallel, it's going to be 90, right? But we don't know for sure if R and S are parallel. Looks like they are, but we don't know that for sure, okay? Same thing with M and N. If M and N are parallel, if this is 90, then this would be 90, right? But because these two are in opposite corners of one another, and because we don't know if either one of these pairs of lines are parallel as of right now, then we don't know this for sure, okay? And I'm going to draw you a picture here and kind of show you. Now, that's why I've said this many times, and I'll continue to say this. Sometimes pictures can be deceiving. Yes?
There is still if you do the vertical angles thing, it's so since each of the sets will make 180 degrees, so then if we already know that 2 are 90, then you just divide the remaining 2 by 2 and then to make 180. So we know that each of the places are, we know that all the angles around the marked angles are 90.
So we know all these are 90, right? We know all these are 90. Do we know for sure if all of these are 90?
We can do a similar thing to what we did on the previous one.
Okay. What if I drew this picture? Here's R. Here's M. Okay. And then here's S. And here's N. So, if I redraw this picture a little bit, are M and R still parallel? I mean perpendicular? Are N and S still perpendicular? Are R and S parallel? What about M and N? Are they parallel? No. So do we have the same information as we have over there? Yep. Okay. But now are these lines parallel? No. Okay. So the way that they draw the line is definitely tricky, right? And could those lines be parallel? Yeah, they probably are parallel, the way this originally is drawn, okay? And that's what's so hard about this. And sometimes they'll draw pictures like this to throw you off, right? It's kind of dirty, a little dirty trick, right? That the book will throw you a picture in here. They look like they're parallel, okay? But that's why, can I draw it a different way where I have the same information where that information is not necessarily true? Okay. Anna, question? Oh, you're just, okay. So yeah, it's definitely tricky. It's kind of hard to comprehend, but if you redraw it, I think it's a little bit easier to see where it doesn't work. See you, Xander.